Hello folks, this is Ray. I'm coming to you from my office, and I'm going to record some information about section 2.5, where we're going to take a look at equations of lines and planes. The list of objectives for this particular section is quite long, and but for this particular video we will just focus on the first objective, which is to find an equation of a line. Now when we think of a line, we think of a point and a slope, and or 2 points, but generally when we come to finding an equation of a line, we think of a point and a slope. In 3 dimensions, the idea of a slope doesn't quite work anymore. The idea of a slope works, it makes sense in 2 dimensions. When we talk about rise over run, the rise would be going vertically and the run would be going horizontally, and those are the 2 dimensions that we're talking about. But when we're talking about lines in 3 dimensions, that idea doesn't quite work anymore unless you can refine it to make it look like it's something that you're looking at in 2D. But in general, 3-dimensional lines cannot just be expressed with a slope. And so the way we're going to find an equation of a line is with 2 things. We're going to look at the point, and instead of a slope that only gives a 2-dimensional direction, we will look at a direction vector that is actually given in 3D. Okay, so let's say our point was equal to x naught, y naught, z naught, and then we have direction, let's call it ABC, as a vector. Then we can write our expression for the line in what we're going to call vector form, and that is going to be the r naught plus d, the direction, times some parameter t. So the idea behind that is, let's see, if we take a look at our xy plane, this is our x, this is our y, this is our z. I'm sorry, if you look at our x, y, z space in 3D, and let's say we're given a point, and let's say the point was r naught. Let's put the point over here somewhere. So that's x naught, y naught, z naught. That's the point. And then we're given a direction vector for the line. So let's say our direction vector maybe looks like this. So the idea of this r naught plus d, and then scale that d by some parameter t, will tell us that we're going to first, to draw this line, we're going to first draw the line going to that point. So this is your r naught. And then we're going to add the direction vector to it. So we'll take that direction vector and move it. And then here is our new direction vector. Now, depending on what the value of t is in our scenario, we will be some point on the line. So if t, let's say, was equal to 0, then you have r naught plus 0, so that just gives you this point x naught, y naught, z naught. When t is equal to 1, then you have the point plus the direction. So remember, the point plus the direction, you draw your triangle, or it would be a diagonal of that parallelogram. And so you will be at this point if this is equal to 1. Now, if t was any other number, then you would be somewhere else, and hopefully somewhere else that's going to be on the line. So let's say what if t was equal to 2? Then I will start over here at x naught, y naught, z naught, and then I will have 2 times ABC. So ABC, that's stretched out twice as long, will give me another point. And if I was -1, if t was -1, then it's going to be x naught, y naught, z naught plus the negative direction of this of this vector d, and then I would be at some other point over here, t is equal to -1. And of course, fractions would put you somewhere in between here, and larger numbers would get you longer. So essentially, you will have a line in 3 dimensions that would be passing through the point x naught, y naught, z naught, and in a particular direction of d, whatever that is. All right, so that is the way to express your line in vector form. Now, if we want to find the line in another form, and this other form actually is more useful for us, this is called the parametric form. It would be like the parametric equations. It'll be x equals something and y equals something. But now, since we're in 3D, we'll have x equals something, y equals something, and z is equal to something. And the way to obtain that is to simply gather all the x components and then set that equal to x. So x will be equal to x naught plus a times t. So that's x naught plus a times t. And then the y component would be y naught plus b times t. So that's y naught plus b times t. And then the last component would be the z component, and then c times t. And so there is your parametric equations. So the set of parametric equations give you specific functions for x, for y, and for z separately, and then that way you can describe your line. So parametric equations work that way. So this has of t in it. This t here is not really that important. We can probably take that out if you want, but I left it there because we know that each of these are functions of t, and t is your parameter. All right, now the last form is called symmetric form, which I don't think it's used much, but sometimes people would like to get rid of the parameter t. We've seen a case where we were interested in getting rid of the parameter to express our equation in terms of x and y. You can do that kind of in the same way in 3 dimensions by doing the same thing what we did before. So you would take your x of t function, and then you would solve for t. And once you solve for t, then you have an expression where you say t is equal to that. Well, if you do the same thing for the y and solve for t, then your t is also going to equal to something with a y in it, and similarly your t is going to equal something with a z in it. Now you've essentially set t equal to a bunch of things, so you can set those bunch of things equal to each other, and now we have what we call a symmetric form of the line. All right. A couple of notes for these equations. These equations are not unique. That is to say, if somebody gave you a different direction but still describing the same line, you could still have the same answer, except your answer would look different from somebody else because somebody else used a different direction. If you use a different point, as long as it's on the line, it would also look different because your equation would look like it's something based on the point that was given and the direction that was given. So you know how you write y equals mx plus b, and when you simplify that, that is a unique form of the line that you are giving. Well, it turns out that when you're doing this in 3 dimensions, your equations are not going to be unique. And also, if you have a given line, you should be able to extract the point and the direction, or you should be able to extract a point and a direction that is representative of that line. So if you have it in symmetric form, you'll see that the components for your direction is in the denominator, and you have x minus x naught, y minus y naught, z minus z naught, which is the point that's on the line that was used to come up with that line. Also, you can see the point here in the parametric form, x naught, y naught, z naught, and then you can see the direction ABC. And of course, the easiest way to interpret or to extract a point and a direction from a line is that if you're given your line in vector form, because the point is clearly given here, and then the direction is the vector that's multiplied by your parameter t. All right, so that's the setup. Let's do an example. Here are 2 points, and if you want an equation of a line passing through these 2 points, I don't have a direction. Remember, the 2 things that you need are a point and a direction. So I have 2 points. I need to find a direction out of that. So let's say our direction vector. To get our direction vector, we'll say D is equal to, and then let's draw a vector between P and Q. So PQ, and we know that this is a subtraction, head minus tail. So the head is Q, so I'll have 2 minus 4. I believe that's negative 2. 3 minus 0, and 1 minus 5. So here is my direction for that line. If you would have subtracted a different way, you would have gotten a different answer. And now we have another choice. I will choose my point to be P, and of course you can choose Q if you want, and then you'll have a different answer from my answer. So like I said, your equations are not going to be unique, but if you're clear about what you're doing, then it should be okay. So we'll use this point for our point, and then therefore our vector form of the line, I'll call r of t, and r with an arrow on top because it's a vector, and that would be the point 4, 0, 5 plus the direction vector negative 2, 3, negative 4 times t. Okay, so this is your vector form. If we want the set of parametric equations, I can take this the x components and then put them together. I have a 4 constant, and then the x component here is negative 2 times t. And the y component would be 0. So I won't write that down. I just have a 3t. And then the z component will be a 5 minus 4t. So now I have a set of parametric equations to represent my line. All right. Finally, if I want to express this in symmetric form, what I would do is I would take the first equation here, x, and solve for t. So given that equation and solving for t, I will get x minus 4, and I will divide by negative 2. So t is going to equal to x minus 4 divided by negative 2. And then for the second equation here, I will get t is equal to, well, I think that's just y divided by 3. And then for my last equation, I will get t is equal to z minus 5 divided by negative 4. So I can take those 3 equations, set them all equal to each other to eliminate the parameter t. I have x minus 4 over negative 2. You probably could have multiplied this by a negative 1 on the top and the bottom and get 4 minus x over positive 2 if you want. And I have y over 3, and then I will have z minus 5 over negative 4. So here are my symmetric equations. And I think at this point it would be a good idea to actually see what the graph looks like. And I want to go back to this drawing of this idea of tracing out the graph of the line. So I started my my graph already by drawing a few things. If I could find it. In a second. Here we go. Let's see. Let's start off with the 2 points. The 2 points are here. One of them is in kind of maroonish. The other one is kind of I don't know what color that is. Blue-grayish. And this vector, I think this point here is the maroon point is P. I'm going to start by drawing a vector from the origin to that point. And then now I want a vector that connects those two. And the vector that connects those two is -2, 3, -4. Now I already moved that vector so that it attaches to 4, 0, 5. So when I draw it, it looks like that. So let's briefly take away this point first. So right now, this is what I have. I have the maroon point and then this green vector for the direction vector. Okay, now let's actually draw the line, and for that, this requires what's called a space curve. I know it's a line, but technically it's also a curve. And if I want my P, my point is 4, 0, and 5, right? But if I look at my parametric equations, I have to add t times the direction vector. So in the first component, I have 4. I will add -2t because that's my direction vector. So 4 minus 2t. And then the second one, if you remember, it was 0 plus 3t. So I can keep the 0 there, or I can just put 3t. And then the last one is 5 minus 4t. All right. So I'm going to graph this from -10 to 10 for now, and I'll hit show the graph, and this is the line. So the line actually does pass through those 2 points, and it follows through that vector. All right. So even more interesting or cool about this particular program is I can do a trace. Before I do a trace, I'm going to click on the curve settings, and I am interested in seeing the trace point and the trace vector. And let me hide these other things for now. These are other things that we're going to need to look at in the next chapter, in chapter 3. But for now, let's just do that trace. And if I ask this to trace, what I have is a drawing vector. I'll call it a drawing vector. A vector that starts at the origin and goes to the point, and it's going to go through every single point on the line depending on my value of t. So when t is equal to 0, I am at that point. When I move this to t is equal to 1, you can actually see it being drawn out already. This is 1. I'm not hitting 1, so what if I just type 1? So at 1, enter, I'm going to be at that second point. If I have 1/2, 0.5, I will be in that, oops, I clicked on the wrong thing, sorry. 0.5, I will be at this point between the first point and the second point. If I put 2, I will be like 2 vector lengths away from my original point. And then if I have -1, I'm behind. I'm 1 vector length behind the starting point. Okay, so if I just let this go and animate, this actually draws out the line from my t-value of -10 to a t-value of +10. And we can't see it because it's further out, but you can certainly play around with this. So I will include this in the notes so you can see it in the notes, but I hope that that makes sense for your equation of the line. All right, to be continued. We're going to continue with chapter 2.5, but that's the beginning. Okay, have fun.